In your pack, you've been given some volumetric equation reactions involving redox. At the start of the pack, you've given your balanced redox equations because it is assumed that you can balance redox equations, and you will also be directed to an earlier video of mine on how to work out oxidation states and balance half redox equations and right fold redox equations. This is assuming you haven't done that yet, in which case you'll need to refer to this page. So let's look at the first problem. So in this problem, two half equations have been given to you, but don't forget you can find the full balanced equation on the first page of this pack. So first of all, it says construct the fully balanced redox ionic equation for the manganate ion oxidizing the Fe2 plus ion. As I said before, this was in my previous video, so I'm going to make the assumption that you're able to balance this. So before you make any attempt on any volumetric equation that involves redox, the first thing is to generate a balanced redox equation. So let's read the question carefully. It tells you that you're reacting potassium manganate, so here this must be the oxidizing agent because it's taking electrons. It then tells you that it's reacting with iron 2. So there's a half equation here for iron 2, and since this is behaving as the oxidizing agent taking electrons, the iron 2 must be behaving as a reducing agent and giving up electrons, so we've written Fe2 because it's reacting with the iron 2 going to form iron 3. I've multiplied it by 5 because you can see that the oxidizing agent requires 5 electrons. 1 mole of the reducing agent, the Fe2, only gives 1 electron, so we multiply it by 5. So the ratio of the oxidizing agent to the reducing agent is 1 manganate to every 5 ions. And that is the important thing to establish, is the ratio of the oxidizing agent to the reducing agent. So as we've already established, the ratio of the iron to manganate is 5 ions to every 1 manganate ion. 5 Fe2 plus ions to every 1 manganate 7 ion. So part B is a very, very simple titration. It tells you that 24.3 centimetres cubed, so that is a volume of 0.02 moles per dm cubed, which is a concentration of potassium manganate, reacts with 20 centimetres cubed of the iron 2 solution. The first thing it wants you to do is to calculate the molarity of the iron 2 ion. So molarity means concentration in moles per dm cubed. So let's do that. So the first thing to do is to take the essentials from the written information above and to put it into a table. So we are told that the volume and the concentration of the manganate is 24.3 centimetres cubed, and we convert that to decimeters cubed by timesing by 10 to the minus 3. We also know the concentration of the potassium manganate, that is 0.02 moles per dm cubed. We've also been given the volume of the iron 2 solution, which is 20 centimetres cubed. With that information, we've got 2 out of 3, and therefore we can now work out the amount. Don't forget to tell the examiner what you've done there, and the amount is number of moles times the concentration, is the concentration times the volume. So that's 0.02 times 24.3 times 10 to the minus 3. Now moles tunnel across, and the mole ratio is 1 to 5. So we need to times this amount by 5. Now we have got the amount of iron, we've got the volume, and now we can find the concentration. The concentration, or the molarity, of the Fe2 plus, the concentration, remember, is number of moles divided by the volume. So before we go to our calculators, let's see if we can simplify this. So we've got 10 to the 3 on the top, 10 to the 3 on the bottom, they will cancel out. So now we can go to our calculator. So on my calculator, it comes out to 0.1215. Now, let's look at the greatest number of significant figures. And we can see here that's 3. So that would round up to the concentration being 0.122 moles per decimeter cubed. Now, let's look at part C. And part C requires something called storyboarding. So it's always a good idea to know the apparatus that you're working with. So what we've got is 1.51 grams of steel wire. Now steel wire is impure iron. We do not know the exact mass of iron in the steel wool because it's impure. We're dissolving that in an excess of sulfuric acid. So what is produced when the iron dissolves in the sulfuric acid? Well, the Fe gets converted into iron 2 sulfate. And that means the Fe has changed into Fe2 plus ions. Now, the Fe2 plus ions have been now made up into a standard or volumetric flask. So we're now making a standard solution of our Fe2 plus ions in 250 centimetres cubed in our volumetric flask. In order to be able to repeat titrations, we can now take 25 centimetre cube samples in a pipette, and the 25 centimetres cube sample of the iron 2 plus is now placed in our flask. Now that is pipetted into the flask and it needs 24.5 centimetres cubed, 0.02 mole per dm cubed of potassium manganate for complete oxidation. So coming out of our burette is potassium manganate solution. Now potassium manganate solution is purple, and when it enters the flask, the Fe2 plus ions are so pale green they almost look colourless. So as soon as the manganate hits the flask, the Fe2 plus ions react with it and remove the colour. At the end point, when their last Fe2 plus ion is oxidised, the solution will remain a very pale pink, as there is an slight excess of MnO4 minus ions, and we get a pale pink tinge. So what are we being asked in this question? We're actually being asked calculate the percentage of iron in a sample of steel wire. Now we have the mass of the impure wire, so if we can find out the amount of iron in the impure wire, we can work out its percentage purity. So again, we need to go back to our redox reaction, and we need to remember the ratio of the oxidizing agent, which was the MnO4 minus, to our Fe2 plus ions, which, if you can remember, was a ratio of 1 MnO4 minus to 5 Fe2 plus ions, a ratio of 1 to 5. So now, if we know the amount of manganate in our flask, because we know its concentration and volume, so we now know that the amount is the concentration times volume, we know the amount in 25 centimetres cubed, and therefore we can scale it up to 250 centimetres cubed because there are 10 times as many moles. And since we know the ratio of manganate to iron, we now know the number of moles of manganate in 250, and what we can now do is scale that up to 5 times. And now we know the number of moles of iron, we can find the amount. Let's do that step by step. The first step that you must do in any redox titration is to get the ratio of the oxidizing agent to the reducing agent. In this case, the oxidizing agent was manganate 7, and for every 1 manganate 7, there were 5 moles of Fe2+. The next step is to work backwards. We work backwards because that always tells us the most information, because we've got a volume and we've got a concentration. So in our standard solution of manganate, we know the exact number of moles, because that is equal to the concentration times the volume. So the next step is there to use the mole ratio from our balanced equation, from the redox equation, to find the amount of the unknown in the conical flask. So the amount of iron is going to be 5 times the amount of manganate, and using concentration times volume of the manganate, there's our volume, and we need to convert that to decimeters cubed. So we need to times our 25.45 by 10 to the minus 3, don't forget this, to get it into decimeters cubed. So that is the concentration times the volume, which gives us the number of moles of iron that was in our 25 centimeters cubed. Step 4 is we scale it up to the amount of the unknown in the volumetric flask. So that was all of our Fe2 plus ions that were transferred in our volumetric flask. So we took out a tenth, and therefore we need to scale it up 10 times to get the amount that was in the volumetric flask. So that's in 250 centimeters cubed. So we now times the number of moles that was in 25 by 10. So we now have the exact amount of iron that was dissolved in our volumetric flask. All that we need to do now is convert that to a mass. At the start of the booklet, you were told the relative atomic mass of iron, and you were told that the relative atomic mass of iron is equal to 55.9. So therefore, if we know the moles and we've got the relative atomic mass, we know that the mass of iron in the wire is equal to the amount times by the relative atomic mass, and that is equal to 1.422655. I'm not going to round down just at this point, and we were told that the mass of the impure steel wire was 1.51 grams, and the mass of iron that's present in there is this, 1.422655. So all that remains now is to find out the percentage purity. So the percentage purity is the mass of the pure divided by the mass of the impure. In this case, that's the steel wire with all sorts of other elements in there, times by 100. And the answer to 3 significant figures is 94.2%, which makes sense because steel is nearly all iron.